people work well out to the end. So it was so nice. He is willing to give us another talk now. We started already with a bit of technical difficulties, but I guess everything will go smoothly from now on. Thank you. Please.
Okay, so we're ready for me to to begin. The room audio is a little difficult for me to hear. Okay. So yeah, thank you for inviting me again to see if I can actually finish this talk after the troubles that we had last time. And yeah, I should have not chosen the first slot of your seminar series yeah, this academic year, because yeah, there's still the teething issues of technology. But hopefully next week you'll have no trouble getting everything to work, and hopefully for the rest of this talk everything will go nice and smooth. So this talk is yeah, very similar to the one I attempted to give previously. So I'm going to yeah, discuss what I understand by BV formalism and what that means to me, because that might be quite difficult, sorry, not difficult, different from people who are more physics oriented than I am. I'll define several things that are all related to Lie algebras or L-infinity algebras. There's a few different types that I'll actually get into, and I'll present I'll be able to do some things for L-infinity algebras. And possibly, but it's unlikely that I'll get there. I'll see how this relates to the famous homotopy transfer theorem for L-infinity algebras, which is some more recent work that's close to being finished, but there are a lot of open questions in that yeah, I'm not 100% happy that they haven't been answered. And so I'll present what those are today as well. So just so you know what I'm talking about and how my notation and my conventions are all working, things that I'll be talking about, all the spaces, the vector spaces, they're going to be real vector spaces. They're all going to be super graded, i.e. Z mod 2 is the grading. And I'm going to refer to homogeneous elements of degree 0 as even elements, and those of degree 1 as odd elements. And I'll use the standard notation of using the vertical bars to denote the degree of an element when it is defined. So just examples, if you're unfamiliar with the supergraded case, the real numbers, they form a one-dimensional supergraded vector space where everything is of even degree. It's just sitting there in degree 0. If instead you put the real numbers into degree 1, so you make everything odd there, we end up with this capital pi of R, and this actually defines an endofunctor on the category of supergraded vector spaces, where you take a vector space, you take its tensor product with this odd version of R, and it has the impact of swapping degrees of vectors. And I will just use this shorthand here, this pi v, for when I'm applying that functor. And that will appear in a few places, and it's mostly just to make the numbers work out in a few places with formulas and things like that. There are also some more technical things that you could sort of get away with not understanding fully to begin with, but when you want to get into the nitty-gritty, they need to be there for technical reasons. A lot of my vector spaces are what I call pseudo-compact. That's where they're given by a projective limit of supervector spaces of finite total dimension, so finite in both even and odd subspaces. And having taken a projective limit or inverse limit, this endows your spaces with topologies. And so in these cases, when I'm talking about maps, they're going to be assumed to be continuous as well. So in particular, when I take duals of such spaces, I mean the continuous dual. But all this setup basically means that we get nice properties that we kind of expect or would hope for when we've gone from finite dimensional spaces and upwards. Things like the double dual being isomorphic to the original space. That happens, and compatibility of the tensor product with taking the dual, for example, that happens when I force taking continuous duals of pseudo-compact vector spaces. Now, the main example of the pseudo-compact algebra that we'll be talking about in this talk is the completed symmetric algebra on a vector space. And essentially, the way that I like to think about this is completing it means we're taking a direct product, and it's the same as the difference between polynomials and formal power series. When you have a polynomial, everything is finite. As soon as you go to power series or formal power series, you're now allowing these infinite combinations of things, and we're not necessarily worrying about convergence of things when it's formal. At times as well, we'll need to assume something about our Lie algebras or our differential graded Lie algebras. They'll need to be what's known as pro-nilpotent. Again, this is just, they are a projective limit of certain things. They're a projective limit of nilpotent differential graded Lie algebras. Right, so that's loads of assumptions and notation and things like that thrown in there. Now we're going to talk about a little bit of formal symplectic geometry, where essentially the geometry is what's influencing the constructions, but I'm very much sticking to the realm of linear algebra. So an odd symplectic vector space is a supergraded vector space where we've got a bilinear, skew-symmetric, non-degenerate odd form as our additional piece of data. And so here this is kind of acting as our symplectic manifold, but the manifold is a pretty boring manifold. It is just a vector space, but that's where the geometry comes from. And then, as we do a lot of the time in geometry, we don't study the object itself necessarily. We study the algebra of functions on that space. And so the algebra of functions on this odd symplectic vector space is given by the completed symmetric algebra on the pi of the dual. So here we need to take pi to get the degrees to actually work out properly. The fact it's the dual gives us functions. The fact that we're taking the completed symmetric algebra is where we're getting this formal construction from. And if our vector space V also has a differential, which say is denoted by D, as they quite often are, this induces a canonical differential on the symmetric algebra or the algebra of functions. And by an abusive notation, as is fairly common again, we'll denote that by the same symbol, even though they are not the same thing. One is a corresponding differential. We're using the same notation. Now, depending on how much symplectic stuff we've done, we might be aware that every odd symplectic vector space has dimension 2n for a natural number n, and there exists a canonical basis where you've got some x's and some corresponding x's, where the x's are of even degree, so degree 0, and the x's are of odd degree, degree 1. And this canonical basis allows us to write the symplectic form in the canonical form where we're summing over these dxi's, dxi's. And this, what's the word I'm looking for? This induces an operator typically denoted by a delta, known as the BV Laplacian, on the algebra of formal functions. And it's just given by these, as it's written there, as the sum over these partial derivatives, where again, we're just pairing together this x and a corresponding c. So it's all quite nice, and you have all this kind of very nice structure sitting in there. And as an output of how this all comes together, we start seeing that there's this very rich algebraic structure in this. The BV Laplacian defines what's known as a differential graded BV algebra structure on the algebra of formal functions. And within that, there's this odd Poisson algebra where we define a bracket that is written on the slide. And so this is not necessarily super important for us to go into, but it's just giving the idea that there's a lot of structure in these things. There's a lot of beautiful algebra in this formal geometric setting, even if we've kind of not done as much geometry as we would maybe normally do. Okay, so let's talk about master equations. So we're now considering our functions to be slightly extended versions of the previous ones. in that we throw in this formal parameter h bar, which then we write either as powers of h or as negative powers of h, i.e. we're taking Laurent series for our functions. Now again, you can't just do this and hope everything works. There are some things that you need to do. You extend the base field to be formal Laurent series, so you have to add h to your underlying field. You need to extend all your vector spaces, and so taking tensors over R with our new base field allows that to happen. And I will denote the new extended vector spaces with an overline. And we need to extend the BV algebra structure by just making it all extended h and h-1 linear. So we're extending everything, but we're also extending everything in the nicest possible way. And so something that's is I think fairly well known in various settings is that an even function is said to satisfy the quantum master equation if it satisfies a particular equation. Now, the function itself is going to be, as is written here, a formal power series in h, where I've written things here in terms of h bar. So powers of h bar. There are some technical things that need to be said here. So m divided by h needs to belong to a pro-nilpotent ideal. This essentially ensures that the exponential exists. Otherwise, we'll have some problems with it. But yes, the quantum master equation looks like this. So we've got this combined kind of differential, where we've got the differential coming from the non-h bar stuff, and then through adding in the h bar stuff and combining it with the BV Laplacian, we've got ourselves what's known as the quantum master equation. Now, using that expansion of m and expanding out also the quantum master equation, you can turn that single equation into an infinite list of equations where you just take out the constant in h, the linear in h, the quadratic in h, and so on and so forth. And for us, stuff that we want to look at, the constant in h and the linear in h equations, they are important for some of our algebra structures later on. So the constant in h equation looks like this. So it's the d of m naught plus a half the bracket of m naught with itself is equal to 0. And depending on what stuff you've done in the past, you might recognize this equation from other places. And we will talk about this equation later, and so I won't ruin the surprise necessarily just yet. But you might know this as the classical master equation. So we've just got this wrapped up inside the quantum master equation is this classical master equation. And then we've got this other equation, which I don't give a name to, but this is the linear part in h. And here we're combining various parts. We've got the m1 part, so that's the linear and h part of m itself. And then you've also got the BV Laplacian turning up because you've already got a h showing up in there. Okay, so the classical BV formalism, or at least as I understand it, this is when you're working with an exact symplectic vector space. So exact in the sense that it has no homology. And I'm taking V to be that vector space and its pairing to be denoted by angled brackets. Now it's algebra of functions for some technical reasons related to operads, which I personally don't fully understand. It could be given what's known as a weight grading, where you assign the weight 2g plus n to a term of the form fh to the g. So the g part is coming from just the power of h, and f itself has degree n in terms of the formal algebra of functions and its standard grading. And we'll let this fractor h of v denote the subspace of this extended formal algebra of functions to be those elements of weight grading at least 2, so greater than or equal to 2. Now, the odd Poisson algebra structure is inherited, The reason that we're actually interested in this fractor H versus the full algebra is because this later algebra is actually pro-nilpotent. And so it would be useful for us in terms of making sure things like the exponential is completely well defined. And the classical BV-Stokes theorem, which could be found, for example, in Schwarz's paper from '93, says if we integrate over a Lagrangian subspace something that's the BV Laplacian exact, so the BV Laplacian applied to a particular function, you will get 0. So this is a well-known result, and it's probably in a lot more places than just Schwarz's paper, but that's one place where I know it is for sure. And it just says these BV Laplacian exact terms, they integrate to 0. So what about the quantum BV formalism? How does that differ? Well, in the classical BV formalism, we've got no homology. We've got vector spaces that are exact, and essentially your differential there is providing an isomorphism from one space onto another subspace. The quantum case is concerned with spaces where the homology might not be trivial. You may actually have some homology. Now, a quick fact, which is actually just a very, very full slide. So we don't really need to digest the whole thing here. But for a vector space, a strong deformation retract onto some choice of representatives for your homology. So you've got an inclusion, a projection, and you've got this S operation that satisfy a whole bunch of identities. This essentially just ensures that we've got a decomposition. And the reason this is important is because finite dimensional vector spaces, they always have this decomposition. So that's really good for us. And it's really useful because it's split things down into here is your homology, or at least the representatives for the homology. And then actually what ends up happening over on this side, so the image of D plus the image of S, this is an exact vector space where things are already decomposed into Lagrangian subspaces. And so essentially this is the part that makes things quantum, and over here you can do stuff that's kind of all the classical bits. And so because we've got this decomposition, we can just perform the classical BV formalism on the classical part and leave the homology untouched and integrate just over the classical part. So it's kind of akin to if you've got two variables in your expression and you integrate over y. So if you've got x and y and you integrate only over y in a definite sense, then you'll be left with x at the end and the y integrates away. And so the effect of this is that if you set things up right, and this is appears in lots of places, but the place that I think I best understood it when I was learning myself is in Costello's book on renormalization. I forget the full title, but it says if you begin with something that solves the quantum master equation M, and then you integrate over it over just the classical parts, and then you take the log of it, and then you times it by h, you get something back that's now still a formal function, but on the homology. But actually, this also still satisfies the quantum master equation. So we can integrate solutions of the quantum master equation on a super vector space to produce solutions of the quantum master equation on its homology. So that's quite nice. We've got rid of superfluous stuff because quite often we're interested in just the homology rather than the whole of the vector space. But we've also noted that within the quantum master equation is this classical master equation and this other interesting equation that we're interested in, even though I haven't really told you why we're interested in it. So the reason that we're interested in these things is, or at least the reason I'm interested in these things, is that they relate to what are known as L-infinity algebras. So just so that we're all know where I'm coming from. A Lie algebra is a vector space that's got a bracket. And that bracket needs to be bilinear, needs to be alternating, and it needs to satisfy the Jacobi identity, which is this identity in the middle right here. And adding a differential to this Lie algebra and ensuring that the differential is actually a derivation of the bracket, so it satisfies the Leibniz rule, this results in what we call a differential graded Lie algebra. And an odd element of a differential graded Lie algebra is said to satisfy an equation known as the Maurer-Cartan equation if it satisfies this equation right here. And we may recognize this equation as something that we saw earlier. This is the classical master equation. So Maurer-Cartan elements from the Lie theory side of things are what, from the physics side of things, are quite often just called classical master equations. And we'll denote Maurer-Cartan elements by this capital MC of V. Now, equivalence of Maurer-Cartan elements can be characterized in a few different ways, but there are two main ways. And as long as you have pro-nilpotent differential graded Lie algebras, then these two ways are equivalent. The paper that I know that has this is Schlesinger and Stashev's paper, which I'm not sure if they actually ended up publishing in the end, but it's one that they wrote and never got round to publishing, but it does have this very useful result that homotopy equivalence and gauge equivalence of Maurer-Cartan elements are actually equivalent in the case of pro-nilpotent differential graded Lie algebras. So I'm going to describe just one of those two. It's the one that makes the most sense to me. I'm going to describe the notion of homotopy between Maurer-Cartan elements. Now, the idea is to introduce extra generators, and those generators are T and dt, and these will give us extra evaluation maps, and then you can evaluate at 0 and 1, and you've got a homotopy between your Maurer-Cartan elements. So it's very close to the notion of homotopy that you're perhaps used to from your algebraic topology classes. So we add to our base field R, T, and dt, subject to the condition that dt is the differential of T. Otherwise, it'd be an odd choice of notation. And we've got these two evaluation maps from RT dt, where we can either set T equals 0 or T equals 1. And we'll use the standard type of notation where we have the vertical bar for 0 or the vertical bar as a 1 for our evaluation. And then for some differential graded Lie algebra, we can throw T or dt, or throw both these extra generators at it by taking a tensor product and extending the evaluation maps to it. So two elements are said to be homotopic if there exists some element of this extended version that's a Maurer-Cartan element of the extended version of the differential graded Lie algebra, and such that when I evaluate at 0, I get one of the original Maurer-Cartan elements, and when I evaluate at 1, I get the other one. And the set of equivalence classes under this relation, and it does form a relation in this equivalence relation sense. This is known as the Maurer-Cartan moduli set, and we just make our MC calligraphic to denote the Maurer-Cartan moduli set. And it's not too difficult to see, but through the BV formalism stuff, if you have a homotopy of Maurer-Cartan elements in your original space and you integrate it, you'll end up with a homotopy of Maurer-Cartan elements on the homology of your space. So you can perform this quantum master equation result that we had before, but it also applies to homotopies, which is good because we want to talk about equivalence of things on these two structures. So Lie algebras are great, and they appear in lots of places, but quite often Lie algebras don't capture enough. They don't capture enough of the theory to actually complete the theory in some sense. And so there are lots of examples of things where extending or generalizing to what are known as L-infinity algebras actually completes the problem. So deformations of associative algebras, for example, understanding those deformations, they can be classified by L-infinity algebras, and Lie algebras doesn't quite go far enough. So what are these L-infinity algebras? Well, they're also known as homotopy Lie algebras, but I personally prefer saying L-infinity algebras. And the idea is that you take the Jacobi identity and you allow it to no longer be holding on the nose, and instead it holds up to a homotopy, hence the homotopy Lie algebra name. And so where is that homotopy given by? It's given by a 3-array operation, so a 3 bracket. That 3 bracket satisfies some identity that's exact up to a 4-array operation, and so on and so forth the whole way up, which is where the infinity comes from. So you could potentially have your bracket, a 3 bracket, a 4 bracket, and so on and so forth. So an L-infinity algebra is a graded vector space with a whole list, a potentially infinite list of multilinear maps, which I've denoted here by L sub n, from Vn into V. And there's a whole bunch of interconnected conditions that you need to satisfy to get up there with the first, well, from L2, that's Jacobi identity up to the 3-array operation. Now note, quite often, and as I've done on this slide, people wrap the differential up in these multilinear maps. So D is L1. I'm going to keep the differential separate, but not everybody does. And so if you read about these things elsewhere, there might be this slightly different choice being made. Now, an infinite list of things is quite daunting and quite useful for us as well as just wrapping things up, is that you can take this infinite collection of multilinear maps and equivalently wrap them up into a single derivation on the algebra of formal functions. And this algebra of formal functions is where we've been talking about doing this formal geometry. Now, I'm not going to go into all the details of how these multilinear things all get wrapped up, but they get wrapped up into a derivation, and then for it to actually be still giving us an L-infinity algebra structure, is it needs to satisfy the Maurer-Cartan equation. Or in terms of the BV formalism, it needs to satisfy what is the classical master equation. And because it's given by a Maurer-Cartan equation, we can do our business of looking at equivalence of Maurer-Cartan elements under the homotopy relation. And this actually coincides with quasi-isomorphisms of L-infinity algebras, which are quasi-isomorphisms on the multilinear map side. And so you can study L-infinity algebras simply through studying Maurer-Cartan elements on the algebra of functions, or in the derivation of the algebra of functions. So this latter interpretation of L-infinity algebras is good for us, because as I've said, the Maurer-Cartan equation is the classical master equation. And so the question that was posed at the beginning of this collection of work is, can I use, or can we use, the rich theory of BV formalism to study Lie algebras and L-infinity algebras and all related kind of structures? Now, before we get to the answer, and the answer is in the positive, otherwise I wouldn't have much to talk about, I'm going to talk a little bit more about some other types of L-infinity algebras, because I'll need them to talk more about the story. So extending the definition of an L-infinity algebra leads to what's known as a unimodular L-infinity algebra. So this is a pair of things as opposed to just one thing. It's a derivation M on the algebra of functions that satisfies the Maurer-Cartan equation. So there's your kind of classical L infinity part. And then you've got f, some formal function that satisfies another equation linking it to this derivation m as well. And here, the nabla is the usual divergence of a vector field. So here the derivation, we can think of as a vector field if we're trying to keep things in that geometric way of thinking. If you want to read more about unimodular L infinity algebras, I think possibly the best place to go to is Braun and Lazarev's 2015 paper. But yeah, for us, knowing the definition should be enough really to go into things. There is one other thing I need to tell you, and that's what's known as a strictly unimodular L infinity algebra. So essentially, all you do here is you forget about the formal function. Then that equation that we just had on the middle of the previous slide now just comes to the condition that the divergence of the vector field is equal to 0. And these are known as strictly unimodular L infinity algebras, and they will show up in our work. Now, once again, having too many objects is not useful, or at least not helpful for us. We'll lose track of things, and we're fortunate enough that the maths works out that we can wrap these things up together by just putting them in the right kind of setting. In particular, we can take the two bits, the classical master equation and that extra equation that was a couple of slides ago, wrap them up into a single Maurer-Cartan equation on this particular space here. So we've got a semi-direct product of our derivations with taking pi of formal functions, where here the formal functions are non-constant. That's what we're saying here, where there's greater than or equal to 1, they have at least some copy of pi of joule v. And the differential that's on this differential graded Lie algebra is given by two parts. It's given by d, that's already there, and then this dE, which is 0 on the functions, and it acts on vector fields by a slight tweaking of the standard divergence. And once again, this differential graded Lie algebra is pro-nilpotent, and so it is well behaved for us. Now, something that's a bit of a shame about unimodular L infinity algebras is that there's no notion of quasi-isomorphism for these algebra structures. That doesn't mean that there isn't one that's just not found yet. It just means we don't know of one. And so the fact that there is no notion of quasi-isomorphism means we have to use this equivalence of Maurer-Cartan elements to actually come up with an equivalence of structures. But it's also, as we possibly will see right at the end of today's talk, it means that certain theorems can't necessarily be extended to the unimodular case until we have that notion of quasi-isomorphism, that notion of weak equivalence. Another flavor of L infinity algebras are what has been coined as quantum L infinity algebras. Now, these live in that fractor H of V. So remember, this is where we've got this weight grading on the formal algebra of functions. And it's an element that satisfies this master equation looking thing, which is a Maurer-Cartan equation when you're looking at things through the Lie lens. Now, sitting within an a quantum L infinity algebra are both standard L infinity algebra structures and unimodular algebra structures. And also, the Maurer-Cartan equation is equivalent to the quantum master equation that we saw way back when I was looking at this BV formalism stuff. So if you take, I think the easiest way to see the equivalence is if you take the bottom equation and you expand the exponential into its usual power series, and then you expand that a little bit and then pull the exponential back out, you'll get the top equation. as being a factor. And so when one is 0, the other one is 0. And so what this means, if we apply the BV formalism to our quantum L-infinity algebras, we get this result here. So this is not really saying too much new in itself, because it's just a reframing of that well-known result published in Costello's renormalization, for example. But it says that given a quantum L-infinity algebra structure M on a vector space V, the derivation that we call here M prime, where we do integrating, taking the log, and then multiply by H again, this defines a quantum L-infinity algebra on the homology. So we can take a structure on the whole vector space, integrate away the exact part, and be left with a structure, algebraic structure, on the homology itself. So we can throw out almost the bits that aren't particularly interesting or useful. So this is good. We can get rid of some things, but how is that new structure on the homology actually related to the one that you started with? Really, they should be related to each other. They should be equivalent structures in some sense. And that's where this minimal models stuff comes in. And the minimal model of an L-infinity algebra structure is technically what's known as, yes, it's just an equivalent structure that's only non-zero on the homology. So they both live on the same space, but the minimal model evaluates to 0 on the non-homology parts of the vector space. And so, a theorem of my paper with Christopher Braun in 2018 says, if we take that integral, we compose it with the natural inclusion from the homology back into the original vector space, then they do produce equivalent quantum L-infinity algebra structures. And so it provides the minimal model. The natural question then out of that, saying, okay, we've found minimal models for these quantum ones. Can I use a similar mechanism to actually prove a similar thing for classical? So what I'm calling classical here, but L-infinity algebras without anything extra, and or their unimodular versions. So in order to get to an answer of this question, we have to do some doubling and halving business. Now a super vector space, it has two doubles. It depends on whether you want the double to be even symplectic or odd symplectic, essentially. There's what's known as the even double, where you take the vector space and its direct sum with the dual, that's the even, and the odd double is where you take the direct sum of the dual with pi of the original vector space. And then there's a natural pairing between these two elements of the direct product, or sorry, the direct sum. And it is essentially just the evaluation product. And very simple construction, but it gives us, even from something that's not got anything symplectic related to it, suddenly throws in symplectic stuff that's either even or odd, depending on if you take the even or the odd double. Now, things don't stop there. These doubling of the vector spaces themselves, they induce doubling, or they induce derivations on the algebra of functions on the doubles as well. And these doubling constructions, they induce differential graded Lie algebra morphisms as well. So not only can we double these things, we can double them in a way that's compatible with our L-infinity algebra structures. And that's really important for what I want to do, is I want to keep this L-infinity algebra stuff all working out nice and nicely. In fact, there's actually a link between these L-infinity algebras. If I take an L-infinity algebra structure on a vector space V, construct its even double, what I'll end up with is a strictly unimodular L-infinity algebra structure on the even double. So I begin with a L-infinity algebra, I double it, and I've now got unimodular L-infinity algebra structure, and a strict one at that. Similarly, if I take a unimodular one and I double it, I'll get a unimodular algebra, and that unimodular L-infinity algebra easily extends to a quantum L-infinity algebra, but a quantum one that doesn't have a particularly long expression for for its structure. It's got a constant in H part and it's got a linear in H part, and it doesn't go any higher than that. And all of this doubling business is compatible with homotopy. So if I take equivalent structures and I double them, I end up with equivalent structures just sitting in a larger space. So I can take L-infinity algebra structures, I can quadruple them, so double the double, and that can produce a quantum L-infinity algebra structure. Now, something that I haven't fully been able to make sense of, because I just don't necessarily have a strong enough physics background, is what does all this stuff actually have to do with field theory, in particular BRS-RT stuff and ghosts? It's very clearly very close to that, and so there must be some kind of relation in interpretation, but I'm not fully happy with the stuff that I've looked at, and I haven't looked at it for a little while, but I can remember thinking that, yeah, I haven't made full sense of this, but there definitely is an interpretation of all of this in terms of ghosts, anti-fields, anti-ghosts, and all that kind of stuff. Now, I've talked about the doubling, so let's talk about the second part of this little section of my talk. Let's talk about halving. So as well as doubling things up, you can halve things back down. Halving is essentially done in the pretty naive way of doing things. And because I've done it in the naive way at the moment, I have this problem where my halving is not really a morphism of differential graded Lie algebras, which isn't necessarily a problem for the constructions I make, but it feels like the theory is incomplete at the moment because, there must be some way of making this actually work nicely, completely within the category of differential graded Lie algebras. Now, how do these maps look? They look something like this. You basically, just take something that's in this bigger symmetric algebra, and then you take what is already a tensor and turn it into a tensor. But because we know that the image of our doubling maps is going to sit within a very specific part of these symmetric algebras, things are going to be then in a very particular form, which, depending on how up on your tensor products and how they relate to derivations, these two things here and same and above, they are isomorphic. And so it does take you from this algebra of formal functions and maps things back down to derivations, and it all does end up working out nice just because I know where things are going to land, but it doesn't work as nice as I would hope. So maybe it's not completely clear because I haven't gone into all the details, but from the name, hopefully enough, halving, these halving maps, they're one-sided inverses to the doubling maps. If I double and then halve, I get back to where I started. Unfortunately, not the other way around, which is where there's this current gap in the theory. But where I restrict to images, things are morphisms of differential graded Lie algebras, and they do respect the homotopy of Maurer-Cartan elements, so they work well enough for the constructions, but they're not complete. They are not as well-rounded as I would like them to be. Now, as well as having these halving functions on the algebra of functions, you can take a very similar map that takes from quantum L-infinity algebras and halves down to unimodular algebras, and things look like this. So it's gone from our H space, which has got fairly complicated, and then it's gone down to our G space. Remember where unimodular algebras live, this semi-direct product in here. And so through this doubling and halving business, in some unpublished work of myself, which, as I said, is not finished enough in my sense, and so it's not been submitted anywhere just yet, because I want to tidy things up and hopefully get a more complete answer before I publish it. But if you double, or maybe double the double, do your integration, and then halve, and possibly halve again, depending on where you started, you can provide minimal models for classical L-infinity algebras and for our unimodular L-infinity algebras. Okay, so this all relates, sort of, depending on which L-infinity algebras you look at, it relates to the homotopy transfer theorem. Now, I don't have time to go through the full theory, but essentially, if we take that previous theorem in the classical case, so we begin with an L-infinity algebra, we quadruple, we do some integration, and then we halve, so we halve, so we take a quarter of, then we can recover what's known as the homotopy transfer theorem for L-infinity algebras. And if you're familiar with that theorem, you may know that the theorem says, well, beginning with this L-infinity algebra, we can rewrite the transferred L-infinity algebra on homology in terms of sums over rooted trees. And it actually turns out that these rooted trees, they have a correspondence with the Feynman diagrams that appear in our integrals coming from the BV formalism. Now, at the moment, I can't state a similar theorem for unimodular or quantum L-infinity algebras, because this actually all relies on, the actual statement of the theorem relies on us having a notion of quasi-isomorphism for my L-infinity algebras. But there's no known appropriate morphism for these structures, let alone quasi-isomorphisms. So yeah, we don't know how to define morphisms on unimodular and quantum L-infinity algebras, and so it means that I can't just, I can't state the theorem, let alone try to prove it. But if we were to come up with the correct notion of morphism, then for it to be correct, basically, I would imagine that it would just be, as a consequence of my earlier theorem about minimal models, the homotopy transfer theorem goes through. And so you can then see how it all works. Now, essentially, the way that we can see how this all works is by using a graphical calculus that's based around standard graphical calculi for symmetric monoidal categories. So we essentially take directed graphs, and in the case that I'm using things are evaluated as you go down the page, where objects, they are the edges of the directed graphs, and morphisms, they are acting as the vertices. So here, my example, I've got U tensor V as being my domain, and so I've got U and V as edges coming into F, and then after applying F, that goes through down into W. And if there's no edge, that means we're using the unit of the monoidal product, so the ground field. So if you've got nothing at the top of the page and then just a morphism, that's just the ground field coming in. And a general diagram is going to be made up of compositions of things like I just had on the previous slide, where you just essentially glue the edges together where the objects match up. Now, in the homotopy transfer theorem, the L-infinity algebra is presented in its multilinear map sense. And so we need to reimagine how doubling and halving works in this particular guise. And in fact, it's actually quite a nice little result. But first, the action of the even double, we take a symmetric linear map that looks like this. So it's gone from the tensor product of n copies into just one. This, through applying just duality, becomes an element of the tensor product of the dual n tensor copies tensor with just v itself. And that's the same thing as a function or a map from the ground field into that particular tensor. So pictorially, which I think is quite nice, all that's really happening when you take the even double is the inputs are flipped. They suddenly go from being inputs to being outputs. So they just move their way around on the directed graph. The odd double is very similar. There's just a parity change that goes alongside that, as well as taking the dual. And so then taking the double of the double ends up here. I've had to insert a W to actually make that work. And then the halving is the same kind of thing, just in reverse. So you have to move things from the bottom back up to the top. Okay. So I appreciate I'm running out of time and I need to actually go and teach a class soon. So I'll quickly get to the punchline. Essentially, yes, through this business, you can recover the homotopy transfer theorem that says if you start with a structure denoted in terms of M's, and you've got a strong deformation retract onto its homology, this induces an L-infinity algebra on the homology, denoted by L's, where your maps, so n inputs with one output, are given with sums over these rooted trees where you glue things together like this, where you've got your n inputs, and then inputs are all just given by inclusions. Anywhere where there's an internal edge, you're taking this S. So this is where the form is propagated through in Feynman diagrams. And then at the very end, you project back onto the homology. And these two structures are quasi-isomorphic, and so they are equivalent as Lie algebras or L-infinity algebras. So in summary, the geometric formulation of my L-infinity algebras very nicely links up with the BV formalism, and the BV formalism gives you lots of tools for transferring these L-infinity algebra structures. The story isn't complete. There are gaps for sure, but we're getting there, and things are coming together very nicely. But there are still lots of open questions that I want to answer, and I'm very happy for other people to help me answer as well. But can this doubling and halving actually be interpreted in terms of field theory with things like antifields and ghosts and all that business? Can I make the halving actually differential graded Lie algebra morphisms? And then bigger problem, I think, is what is the notion of morphism, isomorphism, quasi-isomorphism for unimodular algebras and quantum algebras as well? And then another big question is, can we do something similar but now make things non-commutative, i.e. find minimal models of A-infinity algebras, which are homotopy associative algebras? And that is everything that we have time for, and everything that I wanted to say. So I might be able to answer one or two questions, but I do need to run very quickly for my class.
Yeah.
Thank you.
Don't have time for questions, or James.
Yes. Are you able to hear our audio?
So I can hear you, Frederick, but it's
yeah, so
only
if
people close.
Questions, they will come closer to the mic here.
Okay.
All right, so I guess we have time for one or two questions. So if someone has a question, please feel free to ask.
I'm also happy for questions to be emailed me if people have questions and we don't have time for them.
Maybe
Yes.
it's
Maybe that's the better option.
Okay. Oh, and somebody may have said that maybe there is a notion.
Hi James, can I very quickly ask, what is your dream about the halving procedure? How, like, because you are kind of like throwing away all the higher operations in.
Yes, exactly. Yes.
So what is the expectation that should work?
So I mean, there isn't much expectation at the moment because I haven't looked at it enough. That's the honest answer. Essentially, I was saying, okay, nothing is immediate to me, but actually, really, for me to be able to get this to work, I can just throw everything away, and so I took the easy way out, essentially. But there should be some nice way to say, okay, if there is higher structure there, actually, is there a way of somehow collapsing it down nicely, or is that actually genuinely a problem? There is no way of getting things back, but yeah, it's not clear to me, probably because I haven't given it enough hard thought, but I would imagine there should be some way of making these things actually compatible with Lie algebras, differential graded Lie algebras. They should be differential graded Lie algebra morphisms so that I could do everything in the category of differential graded Lie algebras. But at the moment, I haven't been able to do that. And yeah, that just feels unsatisfying, especially when there's such a rich theory here. It feels like the theory is complete enough. I just need to come up with the correct construction. Hopefully that answered the question, even though it's not really an answer. It's just that I don't know.
I think partially. Thank you.
Okay. I do need to go because I'm needed in the classroom immediately. Luckily, it's just down the road, so down the hall.
I guess we can thank you again, and thank you for a nice talk.
Thank you. So yeah, if you do have questions, I'm very happy to take them via email.
Yes, of course. If someone has a question, I'm going to give them your email. And yes, thanks once again for our seminar. Thank you.
And thank you, Martin, for the archive link. Thank you. Bye-bye.
Thank you.